The inverse of an exponential function is a logarithmic function. An exponential function just means any number, any constant to a power, x. A logarithmic function is a logarithm, or log of a number, with a base. So y equals log to the base 3x. We know that logarithmic and exponential functions are inverses, and we can say that y equals 3 dx is the inverse of log 3 times x, because they have the same base, b, or 3 here. If we look at the graphs of these functions, we'll notice properties about them. Let's first look at an exponential graph. An exponential graph is always going to go up, and it's always going to cross at 1, 0. It will also always cross at the point 1b, where b is the base of the function. So if we have y equals 3 to the x, the base there is 3 because that's a constant, and the graph will cross at 1, 3. The negative x-axis on an exponential function's graph is the horizontal asymptote of the graph. An asymptote is a line that the graph will get close to but never actually touch. So the graph is always going to be that curve shape up because it's exponentially increasing. We also know that the domain of an exponential graph is all real numbers. That means any number is possible for the domain, which is all x values. If you look at a logarithmic graph, on the other hand, it has different properties. It will always cross at the point b1, where b is the base. In the previous example, we had log base 3 to the x. So that graph will always cross at the point 3, 1, because 3 is the base. The graph of a logarithmic function will also always cross at the point 1, 0, no matter what the base is. In this type of graph, the negative y-axis is the vertical asymptote of this graph. And the range, which is all y values, is all real numbers. So do you notice anything about these two graphs? I think that they're reflections of each other across the line y equals x. That just means that it's like a mirror was placed along that line, which is just diagonal through the graph, and that they reflect across that line. So that's the axis of reflection, and they flip over that line. That means that we can find the inverse of an exponential function and create the log inverse. If we see just one graph, we can find the other. In this example, we have two functions, an exponential and a log. Y equals 2 to the x, and y equals log base 2x. These mirror over the line y equals x. If we remember that the y-intercept of an exponential function is the same as the x-intercept of a logarithmic function, then we'll be able to know that they're inverses of each other. In this case, the y-intercept of the exponential function is 1, and the x-intercept of the logarithmic function is also 1. So it's the same. Also, we already know that y equals 2 to the x contains the point 1b, where b is the base. Here, the base is 2, and this graph contains the point 1, 2, which it should. We also already know that a logarithmic function will contain the point b1. b is the base. Here we have log base 2x, so the graph should contain the point 2, 1. Does it? Yeah. Now we can tell that they're inverses of each other.